Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
In 1956. Okay, so we have a noisy channel C. That's the basic definition. And what is a channel C? It's this box which eats an input alphabet V on the letters 1 to N, and then spits out some output alphabet U on the other end. Okay, so you send some letter 2, and you get something on the other side. And the thing is, so that's noise, the annoying part. C has a tendency to switch certain letters with other letters. So, and putting it precisely, each input letter in V has a prescribed subset of the letters U, which are possible when you throw C in, when you throw that input letter in the channel. Okay. So everything will be clearer in a slide. But so far, I'll just put Shannon's motivation. Shannon asked what the maximal rate in such a channel is, assuming that you restrict yourself to transmission without error at all. Okay, so you have this channel which confuses certain letters with other letters, and you want to make sure that the receiver knows precisely what the input letters were. And given this constraint, you want to get the optimal rate, which you can. Which you can get. Okay. So here's an example. This will set things right. Let's define the characteristic graph of a channel C. Okay? So this is our input letters. These are our input letters. We have the input letters 1 to 5. And the channel takes I and outputs either I or I plus 1. Okay, this is our example for a channel. And okay, can you see this up there behind? Okay, so as we can see, since the output of I is either I or I plus 1, then I is confusable both with I minus 1 and with I plus 1. Okay, so we have this pentagon form right here, and we write a graph which sort of embeds our information of the channel by connecting two vertices, two input letters with an edge, if and only if they're confusable in the channel. Okay, so this sort of this is a good illustration of everything that we need to know to deduce the optimal rate, as Shannon had noted. And okay, so now we can formalize what Shannon meant by finding the optimal rate. So we want the transmitter, okay, to decide on a prescribed subset of the input letters such that the receiver will know for sure which input letter had been sent when he receives something. Okay, so in this case, we have these 5 letters. We want to pick a subset of the vertices such that, so both the sender and the receiver know what the prescribed set was, the prescribed subset was, and we want to make sure that if he gets, I don't know, 2, then he'll know which input letter it was. So in this case, it's easy to see that what you want to do, the best thing you could do is just pick an independent set. So suppose we choose 1, then 5 and 2 are out, okay, because they're confusable with 1. And then let's assume we pick 4, then 3 is also ruled out, and we're left with these 2 input letters. Okay, so the best we could do when we send a single letter is 2 in this case. We have 2 possible input letters which we can send such that the receiver will have no error whatsoever. So is that clear? Good. Okay, so far it's easy. And so the noise is the fact that some letter that pairs of input letters can be confused. Okay, so Yeah, so the channel is a mapping between the input letters and subsets of the output letters, which in this case, they're the same alphabet. So it's, maybe I should have written here ABCs. And so each input letter is mapped to a subset of the output letters, and two input letters are called confusable if their output subsets intersect. Okay. And by alpha of G, I denote the independence number of a graph G. Okay, so here it's 2. And the usual question in coding theory is, do we benefit from using longer words? Because we usually do. And for that purpose, let's define. So we're still doing everything that Shannon had defined in his original paper from 1956. We define the kth strong power of G as follows. Okay, so it's an easy definition, no need to be alarmed. We connect two distinct k-tuples if and only if they're confusable in each coordinate. So that's the first thing you should remember before looking at the formalities. In other words, we have this graph G, and we want to connect the two k-tuples if and only if in each of the coordinates you have either equality or an edge in the original graph. Okay, so if we take C5, so we had this pentagon in the previous slide. So check out the green square here. We want we had an edge in the pentagon if and only if we had a difference of 1. Okay, I to I plus 1 and I minus 1. So in C5 square, we have a 5 by 5 board, and you want your first coordinate and your second coordinate to be plus minus 1 difference from you. Okay, so all these 8 squares are neighbors of this green square. Okay, these are the neighbors, and these aren't. This is just gray because of technical difficulties. Okay, so so we have these 8 neighbors of the green vertex, and this is how it looks like in real life. So you have these. It looks, if you get far in, if you look at this C5 square from a distance, it looks like induced copies of one graph, okay, of one C5, and then. Okay, so anyway, I won't waste time to explain the graph. The major thing is that when G is the characteristic graph of some channel C, then there's meaning to G to the K, and then two K letter words have an edge in this K power, if and only if the two words are confusable in the channel. So this is very important, because in order to find a difference, the receiver receives two K letter words, and he wants to make sure that they're different. He has to have one coordinate, at least one coordinate, where he can tell the two words apart. Okay, so in other words, you don't have an edge between two words if at some coordinate the two letters are distinct and they don't have an edge in the original graph. In other words, you're not confused between the two words if at some coordinate you're not confused. Okay, so, and this is the negation. So there's an edge if at each coordinate you're confusable. There's an edge if in every coordinate you're confusable. That's all. Okay? Good. So we just moved from looking at the optimum. The optimum for one letter was just to find a maximum independent set of some graph. Now we have K letters. We want to take the kth power of G, and then again look for a maximum independent set, because we want to find a maximum set of words which are pairwise non-confusable. And then Alice can send Bob, can tell Bob, okay, we have this list of 20 7-letter words, and you'll know that when I send these words that you'll know what the right input was. And this bullet shows that that you can always, I mean, this can't hurt you to take longer words, okay? And that's easy because you can just take these two letters which formed an independent set in the original graph, and just take the Cartesian product, okay? So this is block coding. Okay, in other words, is this clear? Good. And the thing is that a strict inequality is indeed possible. Okay? And that's what makes it interesting. Otherwise, it would have been trivial. And we can find examples where taking longer words can benefit you. And I did choose the pentagon. Well, I had some ulterior motive when choosing the pentagon. It's the smallest graph which has such in which you gain something from longer words. And we can, and this 5x5 knight tool on a chessboard okay, this is exactly these words. Okay, 1, 1, 2, 3, and so on. And as you can see, each two words. Recall that this guy's neighbors in C5 square are these 8 neighbors. So each black square doesn't have any of its neighbors in the set. Okay, so you get an independent set of size 5. Okay, where the trivial thing to do was just to get size 4, because this was the best we can do with one letter. Block coding gave us 2 square. And here you gain something. Okay. Finally, we can define the Shannon capacity of a graph. Okay, so we want to take the independent sets of some large words, k-letter words, and we want to normalize them. We want to normalize this number by taking the kth root, because you can always take like 2-letter words and just block code it. So you get you always get an exponential increase, and you want to see what the base is. Okay, and putting it formally, you have supermultiplicativity, because you can get an independent set of k tuples and an independent set of L tuples, take the Cartesian product, and then if you're confusable, if your two words are confusable, if and only if they're confusable in both parts, so you get that this inequality holds. You have supermultiplicativity, and then there's Fekete's lemma, who is Fekete, who is the father of my great grandfather, academic grandfather. Okay, so he's the grandfather of Noga, who's my advisor, a long time ago. Okay, so this shows that the limit exists and equals the supremum. Okay, and okay, what does it mean? It means that you should think of it this way. It's like, I'll put the next two bullets together. Suppose you have your input alphabet is A to Z, okay, and you have some channel, then instead of 26 letters, if the capacity is 7, it means that it's as if you had only 7 letters, but no confusion whatsoever. So that's the idea of the Shannon capacity, because as you use longer and longer code, as you use longer and longer words, suppose k is a million or so, then you can roughly get 7 to the k different words. That's the best you can do as k increases. Because, okay, so you get 7 to the k different words as k is very large. So it's as if you had only a 7-letter alphabet, but your channel was error-free. So that's the idea of the Shannon capacity. And, okay. And some easy bounds on the Shannon capacity, all the way from Shannon's original paper. We already know that C of G is at least alpha of G, it's at least the independence number. That comes from using single letters. And the second bound, the upper bound here by the fractional chromatic number, it's an easy to see bound. Let me just say a word about it for, if you omit the F and just talk about chromatic number, then the chromatic number of the complement is like, it's covering the complement by independent sets, right? That's chromatic number. And then you move to your original graph. It's covering the graph by cliques. So suppose you have your graph G, and then you cover it by cliques. Then an independent set can only pick one vertex from each of these cliques. Otherwise, you'll get an edge. So alpha of G is at most this chromatic number of the complement. And then it appears that when you take the kth product, the kth strong product of G, so if this was, say, 10, then in the kth product, you can cover the graph by 10 to the k cliques. You just take all the Cartesian product of the cliques. So it's something you can verify. And then you'll get that alpha of g to the k is at most 10 to the k, but we're normalizing everything by taking the kth root, so we'll get, again, this upper bound of 10. This was all in Shannon's paper. And the same works for fractional chromatic number. And the smallest graph unsettled by this equality was the C5, which we had previously seen. So in everything up to C5, there's these little drawings in Shannon's original paper. He draws all the graphs up to 5 vertices and writes a small number near each of them. And then he says that and in each of them, the best you can do is use single letters. You gain nothing by using longer words. And then for C5, he saw that you get something, but he had no upper bound. The upper bound for the fractional chromatic number of the pentagon is 5/2. Okay, so it's 2.5, and then there was a lower bound of square root 5, because it's taking the square root out of the 5 achieved in the second position. So square root 5 is 2.23. We have 2.5. That's how it stayed for 23 years. And this bullet here just said that all the perfect graph theory conjectures, the weak perfect graph theorem, the strong perfect graph theorem. So this followed from an attempt of Berge to characterize all the graphs which satisfy an equality here and for every induced subgraph, actually without the fractional, but it doesn't matter. So in 78 and 79, there were first other bounds. It's the first time that other bounds came up for the Shannon capacity, which aren't this chromatic number, algebraic upper bounds, which are useful until this day. And in 79, Latsi-Lovas came up with this with the celebrated theta function, which finally solved the case of C5 and showed that it's indeed square root 5. And this theta function had many, many other applications in computer science, as it's polynomially computable up to any arbitrary precision, and it falls between all these interesting NP complete to approximate parameters. It's somewhere, it's here. It's between the capacity and the fractional chromatic number. So it means that, and both these parameters are NP hard to approximate. And so, okay, enough said. I'll just note that C7, the cycle on 7 vertices, is still unknown. So that's a notoriously, it's not that it's too, it's quite annoying that we can't even say something about a cycle on 7 vertices. And I'll survey some different aspects of the capacity and how it relates to Ramsey theory and to and to questions in coding theory. Questions so far? Okay. So we'll start by looking at this capacity. So we already said that there are cases when one-letter words are optimal. Okay, you can send. Okay, the best you can do is just pick an independent set in the first power. Just pick a set of letters which aren't confusable, and then this is your code. Just to block code it. Okay, and Lovas's theta function gave us examples such as that pentagon on 5 vertices, where 2 letters are optimal, but you can't do anything better than that. Okay, just block code 2-letter words. And I'll just note that we have no other known G which achieves the optimum at any other finite position. Not at 3, not at 4, nowhere. So, which is a bit preposterous. I mean, we have some nice candidates for graphs which should achieve the optimum at the 3rd position. We have this nice, we see the jump achieved at the 3rd position, but then we can't show that it stops there. So, so at the beginning of our study of these Shannon problems, we thought, okay, maybe we can just say that that's taking alpha. So we have these 1-letter graphs, these 2-letter graphs. Maybe if we take all graphs up to position 100, we can say something about the capacity. Okay, we can approximate it somehow. Okay, just say something about the optimal rate, and the next slide will show that this is false. Okay, that's an annoying result. That in fact this result is just a warm up to tell you that this capacity can do crazy things. Okay?
Wait,
and
which order are the quantifiers here?
in the answer?
Well, I mean, if I fix G,
Okay.
then it must converge, right?
So the next slide will show it formally, because this is like okay. This is the precise sentence and the precise theorem. Okay, and so it's as follows. You can fix arbitrary positions, okay, K1, K2, K3, and so on. And given these positions, and you can fix an epsilon, and I can construct a graph, G, this is what you get from words of length K. This is the maximum independent set normalized by taking the Kth root out. So I can make this series have jumps at these arbitrary locations. Okay, so if you look only at this independent series, so you take a graph, you look at what you get from one-letter words, two-letter words, and so on. It's as if you get nothing. By this point, you might have been convinced that this is the right answer, and then there's a jump. And then there was a question that Tom Bowman asked us, okay, what if I see one jump, whether every graph can jump only once? And then we can stop, so we can devise another jump and another jump. And these are polynomial jumps, so everything looks kind of bad, as you can see. And the question is, okay, how high can it jump? I mean, is there any way to bound this behavior? To say something about, okay, I saw alpha G, that alpha of G is, I don't know, 1,000. Can the next power jump arbitrarily high? What can we say? And this is actually related to Ramsey theory, as first noted by Erdős in 1971. So this is a quick reminder of the Ramsey number RKK, which is the minimal integer. There's always the confusion whether you want to take the minimal one where every edge coloring has one, or the largest one such that there exists a... Okay. So we have the minimal integer R, so that if we take the color, so this is now the complete graph, and we color its edges by two colors. This is blue, and this is supposedly red. I don't know how to, maybe I'll no other colors. Imagine that it's red. So we want to...
marker there under your sweater.
Okay. So we color it by blue and black. And we want to find the minimal integer R such that every two-edge coloring will contain some monochromatic KK. Okay, that's our KK. And it's a nice claim. It follows easily that if you have alpha of G which equals 5, then you know that alpha of G squared can't exceed 165. This is yet to be improved. No one knows R. So this is R66. This is the best bound known today for this Ramsey number. And in general, if you have alpha of G equals K, then alpha of G squared doesn't exceed RK plus 1, K plus 1 minus 1. And this is tight. So there is a graph G which has this kind of jump. So it's not just a bound, but these Ramsey numbers have a strong relation to the Shannon capacity. They symbolize the maximal number, the maximal jump that one can attain. And the proof, I won't prove many things in this talk because of the time constraint, but this is an easy proof. So this is all the proof. You just take your independent set of G square. So this is an independent set of G square. Here are vertices. And we consider it as a complete graph. We take the complete graph on these vertices. Okay, so that's just to say that we're drawing all the edges and we're giving a color, either black or blue, to each of these edges. According to the following rule, we had these, so two vertices. This is u, v, and this is u prime, v prime. Okay, so if it's in an independent set of G square, then in one of these coordinates it wasn't confusable, right? So suppose it was in the first coordinate satisfied that u and u prime differ, and there's no edge between u and u prime in the original graph. In this case, we'll color it black. So this was in the first coordinate. We'll color it blue if the second coordinate was disconnected. And if both were disconnected, then pick a color. It doesn't really matter. And now, since this S is of, assuming that S is of size at least rk plus 1k plus 1, it means that we must have a monochromatic kk. So we have these vertices which are all disconnected in the first coordinate because they were all connected by blacks, which contradicts the fact that alpha of g is k. So that's an easy relation. And having seen that, I'll give some open problems which summarize this part of the talk. Okay, so we've seen that any fixed number of powers can't help us approximate this capacity. And there's this partly ludicrous question. Suppose in this construction where we kept seeing these jumps, I didn't tell you that the number of vertices was exponential in all sorts of things. So like in the product of these indices, and it was quite a big graph. And the thing is that you can't hide these jumps for too long. You can hide them as long as your number of vertices is large enough. But we believe that if you look at all these numbers up to alpha of g to the n, or n squared, then you probably know enough to approximate the capacity. And the intuition is like you have these n over 2 bits in your adjacency matrix. So there's only so much. So this is really just n throwing. But there's only so much information you can hide in these entries, which you reveal step by step in each of the powers. And at some point, you're supposed to know enough to approximate the capacity. But this is just to say that this second one, the f of n equals 2 to the n, that's I'm willing to bet a lot that this one is true.
Do you have a negative result? So what you just mentioned, your counterexample, do they
So
prove that it doesn't work for f of n equals log n?
no, nothing. Just k. Because the thing is with these creatures, when you take a power which grows to infinity, then you start having all these dependencies between. We have our original construction. I failed to mention that was a probabilistic construction. And then when you start taking a power which increases with n to infinity, you start getting all these annoying dependencies which we can't handle. So I don't know. No. Yeah.
So when you say can you approximate, I mean, wouldn't you guess that the capacity is just equal to what you get by looking at the last one?
I would guess, but it's always very hard to get Noga to sign on a conjecture. So the best I could was to say that it's a factor 2, or maybe 1 plus 1 minus epsilon, factor 2 for n, and he agreed to write 1 minus epsilon to the 2 to the n.
But you don't.
But I would
something more subtle where you look at the whole sequence and it's some strange.
So exactly. Okay, so I'll just say one thing. Really, exactly, you can't really have, because we have instances where the capacity is never attained. So an easy example, just to think about, is take this C5 and add one disconnected vertex. So it's not. It's relatively easy to see that the capacity is 1 plus square root 5 for this thing, and this number can't be an integer root of any integer. Okay, so this means that you never attain the capacity. Only the supremum is at infinity, but you get really close right after a few steps. So approximate should be the right thing up to. Okay, you get really close after n, but to say formally that it's precisely then.
So no, but even to getting close, right? It seems that you have some subadditivity, and it's not quite that it's monotonic.
That's also a very good note. Yes, so
the last one, I mean.
Yeah, so it indeed looks, that graph which I just sketched a while ago, it actually looks like these because it's sub-additive, exactly what you just said. So, for example, for the C5, without this disconnected vertex, you can do stuff at multiples of 2 because of this block coding, but so you get something at size 2, but then at size 3 you can't repeat this block coding, so you have this, the rate drops a bit and then comes back to, so indeed
but that indicates that you might not need alpha of g up to alpha of g to the f of n, but it should be enough to have alpha of g to the f of n over 2 up to alpha of g to the f of n or something.
Alpha of g to the f of n over...
He's saying that you might not need the smaller, the
probably. Yeah, that was just it was just an easy.
You might not need
I know.
the smaller.
It was shorter for me to formalize the theorem this way. But that's true. You just need the last one up to all the prime factors of f of n. Okay, so yeah. Okay, so and then there are the other problems. Is it decidable to approximate C of g? I don't know. I mean, run as much as you like, just give an answer.
And what if you replace 2 to the n by some Ackermann function?
I'm settling for anything right now. So after a few years, it's all conjectures, nothing. We know nothing. It's quite sad. And let me forget about this one. I can maybe, because I'm slightly running behind, I'll just mention this one.
You started late, so don't.
Okay. I'll just mention this one, which has a $250 Erdős reward, which is today, I think an Erdős dollar is $10 US today, so it's 2,500. But seeing the dollar's value today, so it may not be worth as much, maybe. But yes. But this question is intriguing because, it's by this Ramsey relation we just mentioned, it's equivalent to how fast R3333 k times grows. I won't get into the details, but the thing is, suppose you have this graph which is so dense that every 3 vertices contain an edge. The complement has no triangles, it's equivalent, but every 3 vertices contain an edge. Is C of g at all bounded? Is it 1,000 at most? Is it 1,000,000? Okay, can you get the graph to get some kind of rate which grows within? And this we know nothing about, and this has been thoroughly studied without success. So $250 is quite a lot for Erdős. Usually it's 100 or 200. And but I stated this question because it will relate to something else which we're now going to explore, which is sum of channels. Okay. Okay, so what's a sum of channels? So that's a nice thing to think about. You have 2 guys, okay, and each has his own channel in a different language. So different languages, there's no danger to get confused between these. Look at these Hebrew letters and these English letters. So you're kind of safe when you're sending them. However, Hebrew letters among themselves have tendencies to get mixed up. And so you have a graph which states which letters are confused with which letters, and the same goes to English alphabet. But these 2 channels are completely safe between them. So this is stated here.
So you're just looking at disconnected components.
Exactly. So this is the next bullet. Yeah. So as Jennifer stated, the characteristic graph is precisely the disjoint union of the 2 individual characteristic graphs. And Shannon examined this in his original paper from 1956 and said, okay, suppose that this guy joins me, and remember that C of h is roughly what's the size of your alphabet if you want to restrict yourself to 0 error transmission. So here it's 7 and here it was, 10. Then if that guy joins me, Shannon shows that he can add this 10 to my 7. So we'll get an alphabet size of 17, roughly speaking. And that's very intuitive. So we showed that you can always get at least this sum. And showed that, okay, he conjectured that there's equality here. And actually, he showed certain families of graphs where equality indeed holds. So, for instance, it's all those graphs which satisfy that equality of perfect graphs, which I mentioned a long time ago. Okay. And in other words, how can, okay, a false answer to this conjecture means, how can you, I mean, I have this channel with 7 letters if I restrict myself to 0 error transmission, and you have 10. Now you add your 10 to mine, but each of us are, I mean, these are 2 independent channels. How can you add more than 10 than your 10 which you had independently? Okay, because there's no link between the 2 channels whatsoever. But indeed, the question is false. The conjecture is false, and Noga showed it in '98, and he produced graphs, G and H, so that each of them has capacity at most k, but the sum has an alphabet which exceeds any fixed power of k. Okay, this is more than k squared, k cubed, k whatever you want. Okay.
So is that a probabilistic?
No, so that's, yeah, and I'm going to give an intuition which, okay, so so this is the best way I found to, I mean, this is the essence of the proof, in my opinion. But it's based on a false conjecture. It's not false, it's an unknown, but it's still, you'll get the hang of the proof, because otherwise you'll just, it's easy to get lost in details. So suppose you believe that the random graph has a capacity of log n. Why should you believe that the random graph has a capacity of log n? Well, it has an independent set of size log n, and supposedly, if everything's random, you shouldn't be able to benefit anything, because it's like this weird random structure, and why should things fall in place? So that's an intuition. The best known upper bound is square root n by the Lova's theta function. It took a while to prove that result. And it's widely believed that it's indeed alpha, that indeed you can't do better than the first power, than alpha of g, which makes this log n correct. So suppose you believe me. Okay? Good. Then what we can do is as follows. We take g to be a random graph. Okay? So g is now a random graph on the vertices 1 to n, and we'll pick h to be its complement. Okay, this is g and this is h. Random graphs on 5 vertices produced by Mathematica. So indeed it's random. And so as you can see, since g was a random graph, g and 1/2, and we stated that with high probability it's O of log n, the capacity of O is O of log n, then both g and its complement, which is also a g and 1/2 graph, both of their capacities is O of log n. Okay? So our initial requirement is okay. This k will be log n. Now, what can we do? So I'm now going to show you an independent set in g plus h square, which is large. Okay? And where did I place it? Here. Okay, so suppose we look at this set. We take these i's in n, and we pick all the pairs, I in G and I in H. Okay? Then what do we have? We had this, oh, maybe I'll draw it in this area. And this is, and now I'm considering 2 vertices, I and J. So let's look at the original graph G. If we had an edge between I and J, then we don't have an edge here in H, because H is the complement of G, and vice versa. Okay? So precisely one of these coordinates will be adjacent in these. Yeah. So so we get square root n. I mean, we get n, but we'll have to take the square root because we're looking at the second power. So we get an increase from log n to square root n. Okay, and in the real proof, I mean, Noga does the same, only we can't really handle random graphs with Shannon capacity because of all these dependencies which I had mentioned earlier. So Noga uses a variant of the Frankel-Wilson construction for a Ramsey graph, which is sort of a random graph. And there it's easier to come up with upper bounds because everything is algebraic.
You're using the fact that there's a relationship between
Yeah,
the two graphs.
exactly. You're taking, so okay, in Noga's construction, again, he takes the graph and the complement. So this part is exactly the same. Just this part for G, it's something that you can give an upper bound on. And yeah, so if your language happens to have reverse confusion, an inverse confusion graph, then somehow we can yeah, kind of strange. And by the way, sadly, this is off the record. So that's the only way known today to come up with increases with these jumps in the Shannon capacity. We have no using a so it's either the complement or the sum mod p should be something or but that's the basic trick we can do.
But, I mean, it makes sense that you're not going to benefit if there is no relationship. Between the graphs, and if there is, then
it has,
the sum is great. The whole is greater than the sum of the parts.
Okay, so so how much time do I have until 11:30 or?
Maybe until I don't know, another 20 minutes or.
Sure. Okay.
You're okay with 20 minutes, yeah?
Yeah, I can. Anything between 20 minutes and a day. So I have prepared enough material. Okay. Good. So in this result, we show a stronger result holds, and it's as follows. So I'll let you just look at it for a second. So suppose instead of two guys, you have now t guys. It sounds fairly close. You have t guys, and we can mark a specific family of subsets and call these subsets privileged or good subsets, and form the following situation. Each subset of the users which combine their channels together, they'll have a low capacity if they don't contain one of these good subsets and a high capacity otherwise. This is an example. So suppose this family of subsets, that's always the good example to give, is all the k element subsets of T. Okay? Then you have the following situation. Any k senders combined have a high capacity. Okay, and I'll get into what high is in a minute. Any group of k minus 1 have a low capacity. Okay? So it's like this secret sharing analog, where every k minus 1 can't decrypt, but any k can. Only in this case, we restrict the rate of any k minus 1, and we give a high rate of transmission to any k. Okay, and in particular, this extends the former result because you can take k to be 2, and then you have two graphs. The two of them have a high capacity. Each of them alone has a low capacity. But it also extends to a lot of our other examples. And I think I'll just skip the construction. It's some you have to kind of do a trick, and instead of being of the property that your subset has a member of F, you have to come up with these subsets such that their intersection is empty if and only if you contain a member. It's switching this requirement, and then we take these subsets to be subsets of primes of some ground set. We pick the elements in a nice manner, and then we get. I want to get the bounds right. So just don't be frightened of. I'm not going to say anything about the bullets. The upper bound. This is what small is. Okay. So any subset which does not contain a privileged subset is at most n to the epsilon for any epsilon larger than 0. Okay? On the other hand, any subset of users which does contain a privileged subset, 1 to f, has at least n to the 1 over f rate. Okay, so suppose we stick to the example of F being all k-element subsets, all 5-element subsets. Okay, then the difference is n to the epsilon against n to the 1/5. Okay, and this is some trick with primes and some.
What did you do with the primes? Why was the prime?
Okay, so the upper bound here used polynomial representations over ZQ. This is a bound which follows from the original bound of Hammer's in 1978. He had some matrix bounds, and then a special case is a bound using polynomials. So you need to work over some finite field. The reason we used these sets AI, we wanted to work with sets of primes such that in this case you'll have one prime which belongs to everyone, and then you'll be able to work over that field. Okay? In this case, there's no one prime that belongs to all graphs, so some property has to be satisfied by two distinct primes, and then you can apply the Chinese remainder theorem and show that the product of these two primes is so and so, and so it's a little, it's a little technical. Okay. As a byproduct of this result, we also get the following. So recall that we just mentioned that there's a tight relation between Ramsey theory and Shannon capacity. So from the exact same argument, so this is just a one paragraph proof given the work we done earlier. You can two-color the edges of you can t-color the edges of a complete graph in an explicit way. So there's an explicit construction of a t-coloring such that every induced subgraph has all the colors. Okay, so the original Ramsey statement was there's no monochromatic KK. Even if the original definition of a Ramsey graph on t-colors is there's no monochromatic KK of one color, even if you color it by 10 colors. Here, we don't just want something to be monochromatic, we want it to be multi-chromatic or rainbow, to contain all the colors.
So this statement, the new aspect here is that this is explicit if you randomize a random.
So this is explicit. There's no random here. It's deterministic. I'm just choosing a large prime and
but I'm saying
what can you do?
The aspect here compared to what was previously known is the fact that this is.
So this wasn't.
These parameters, it wasn't known.
So it wasn't known. Okay, so it wasn't known at all, non-randomly. Random is easy. You just color everything randomly, and then.
So if you allow yourself random.
Then it's easy. You just take a random coloring. Yeah, but it's like Ramsey graphs. It's easy to come up with Ramsey graphs, but it's very difficult. And I don't know of any construction that does this explicitly non-randomly. Okay, so I tried to see whether I heard some. I tried to see whether Rao and Avi's new beating the Frankel-Wilson-Ramsey bound, whether it implies this construction, even though you can argue whether it's explicit or not, but that's not for this talk. But it doesn't follow straight from their proof, and maybe after some work. Okay, so some open problems. We sum up this part. So we saw that the sum of two channels of capacity k can exceed any fixed power of k. Okay, and if the conjecture, so you can get to k to the log over log log. If this conjecture is true, you can get all the way to e to the omega of k. We had this jump from log n to square root n. And you can ask two questions. First, what is this expected value? And second, and this is always embarrassing to ask. So suppose you have two graphs and their capacity is at most k. Can you bound C of g plus h with any function of k? 2 to the 2 to the 2 to the 2 to the k. Tower of tower of tower of k. I don't know. Something. And notice, so it's like you have these two graphs. Each of them has capacity 10. And you're trying to get to a capacity which grows with n. And that's why I brought that question earlier, the one with the $100 bill on it. So it said the first power is bounded by 2. Can you get somewhere that grows with n? Here, all the powers of each graph are bounded by 10. Can you get something done with the sum of these two channels? So when you try to attack these problems, they look kind of similar, and hence so is our progress on each of them. But they are, I mean, it should be right. I mean, you should be able to bound it by, I don't know, e to the k. It sounds reasonable because that's how the random graphs should bound the Ramsey numbers, but okay. Okay. So I'll just say a few things about. I'll stick to the introduction and omit the part of the results of this area. Here we, using our methods and tools which we already came by working on the strong graph product, which was everything we discussed so far. We were asked some questions in coding theory. So these are questions for example. So they're representing the class of problems that such an approach can solve. So suppose you have vectors over 0, 1, 2 to the n. And you want to find the maximal subset of vectors such that the Hamming distance is even between every two. Okay, what can you do? Suppose you want the Hamming distance to be odd. Okay, so this calls to define the product quite slightly differently. First, we wanted to have an edge or equality in each coordinate. Now we just want to have an odd number of edges. An odd number of edges. So why is this related? So if you take the complete graph to the k, I'll return to the definition. So what does it mean to have an edge here? It means that the two vertices are different, okay, are distinct. So counting the number of edges and hoping that it's odd means counting the Hamming distance and seeing that it's odd. So an odd Hamming distance corresponds to an edge. And if we want to find the maximal number of vectors of alphabet 3 to the n, we want to find an independent set of this graph. And so an independent set is a maximal number of vectors with even pairwise distances. A clique is a maximum number of a maximum set of vectors whose pairwise differences are odd. Okay. And we wondered how do these things behave asymptotically for any graph, and in particular for the complete graph. And I don't want to forget about these areas. I just want to show that these limits both exist and are bounded by these nice parameters, by n, namely, and the independence number grows exponentially with k. The clique number grows linearly with k. Both limits exist. One grows exponentially, one grows linearly. Okay? So, and this was easier to show. The lower bound was, okay, and this wasn't too difficult to show. This took a bit more work because just think of this graph, G XOR k. It has n to the k vertices.
Is that n plus 1, k plus 1 in the last?
Oh, this is k. I'll just put my finger so you won't see. Okay. I can write on the, okay. So this is k, sorry. I recall telling myself to change it, but okay. The thing is about this parameter, consider the number of vertices of this graph. It's n to the k vertices, but we're dividing it by k. So it takes some effort to show that this thing doesn't explode here. Okay? Here it's much easier. You have n to the k vertices. You're taking the k root out. Nothing can come out too badly. The upper bound is trivial. But here we had to do some work. And I'll just go to the results. Forget about this. Okay. So using spectral analysis, and we got some bounds, and we showed. Forget about this as well. We showed that the answer to, I'll just go to the answer to the original questions. If you have an alphabet of size 2, and you want a maximal set of vectors with even Hamming distances, it's 2 to the n. That's the answer. actually it's 1/2 2 to the n. You take all the vectors with even weight. Easy. Now you extend it to 3. Now it's not so easy to show that because you have that corresponds to a nonlinear code. That's the original motivation. So we were asked whether nonlinear codes can do something beyond this, taking all the binary codes with even weight. And indeed, you can't do anything better. You get still 2 to the n. And even with 4, you get 2 to the n. Okay, so this already looks promising. However, with 5, you already get an increase. Okay, so 2, 3, and 4 letters give you the same number of vectors asymptotically. You switch to 5, suddenly you get a better exponent. You get square root 5 to the n. Okay, and the odd case is very simple. Since we said that this limit is that this thing grows linearly, then it's theta to the n for every alphabet, and it's really less interesting. And now just to finish, we have some extra results on these XOR powers, which and we settled the problem of the asymptotic this asymptotic limit of the clique, but in a more recent paper. Okay, but let's just think of the following notion, which will kind of wrap everything up and connect to the original Shannon ideas. Okay, so think of this XOR power. You don't have to remember its definition. Just think of it as an operator on graphs. It eats a graph, G, and spits out its kth power. Okay? So our previous results, which I hadn't really gotten into because I have no time, show that if G was a D regular graph, then the result is also D prime regular. Okay? And it's not difficult to see that this D prime grows, that the density is roughly 1/2 with large K, because you're kind of asking yourself how many other tuples have an odd distance from me. Okay, so it doesn't really depend on the original density. When K is large enough, this tends to 1/2. Okay? This you'll have to believe me, but I already stated that the clique number grows linearly with the power K. So what does it mean to have a clique number of at most n to the K? Now G is fixed, the graph we began with, and we're letting K grow to infinity. This means that the clique number is logarithmic. It's K times n. K is the log. We have n to the K vertices and nk clique number. So this graph is random looking in the following sense. Its edge density is very large. It's 1/2. However, it doesn't have large cliques. So maybe we could use it to create nice Ramsey constructions. The problem is that it had huge independence sets. We didn't get into that, but this followed from the fact that we're working mod 2. So we have an easy construction for a large independence set. And this triggered the notion of maybe working under, don't read anything, we'll just look at the title, of maybe replacing the mod 2 by some large mod P. And then instead of having square root independent sets, we'll have like the pth root, n to the 1/p. And the methods become much more complicated. We use these Delsart's linear programming bound. This is a lot of work with the Kravchuk polynomials. But it's like this method is always, it's a miracle that it works. You have to find the exact polynomial that fits all these constraints, and then you get a precise bound. So it worked once. And for the others, we have these asymptotical results here and here. And what have we shown? Okay. I'll say one last thing about the P powers in one slide, and this is the one but last slide, and then I'm done. So we've discussed the Shannon capacity on one single channel and sums of channels, and showed that there are problems which relate one to another, and then that everything is related to Ramsey theory. Then I said a few things about the XOR capacities and about wanting to generalize them to P power capacities, to any prime P, replacing the mod 2 of odd even number by some P to maybe motivate us to create explicit Ramsey constructions. And And it so happens that indeed these give explicit Ramsey constructions, and it's related back to the Shannon stuff, as the last slide will show. So our motivation was to create explicit Ramsey constructions. We're good with the clique number. The clique number was good to begin with, taking a prime p instead of mod 2, just increase it polynomially. We only had to worry about independence numbers. And this is the final thing to say. For every g, it doesn't matter which g you start with, as long as it's regular, because I think, well, it doesn't even have to be regular. So for any g, we can point out an explicit large Ramsey subgraph of some of its p powers. So you have this operator, the p power operator. It doesn't matter which graph you begin with. Take it to a high enough p power, and you get at least a subgraph of it will be Ramsey. And if you want it to be a good Ramsey graph, so a Ramsey graph is a graph without large monochromatic subgraphs. If you want it to be a good Ramsey graph, it turns out that you want the Shannon capacity of the complement of G to be large. Okay, so it's kind of, the Shannon capacity is again related to these. We kind of thought we left it behind us when we moved to the p powers. And in particular, when you choose G to be the complete graph, then the best you can do, you write these inequalities, you have to look at this power, and you get a Ramsey construction which is precisely has the same bound of the Frankel-Wilson bound, which is the best explicit construction, which just doesn't involve an algorithm up to this day from 1981. So, and there are relations between this construction and that construction. And so this kind of ties everything in a knot. And that's it. Okay.